Today we'll explore the concept of continuity. We say a function f of x is continuous at x equals a if the limit as x goes to a of f of x is f of a. So in other words, continuity says taking a limit is the same as plugging in. There are three things that have to occur for a function to be continuous at x equals a. The first is that the limit as x goes to a of f of x has to exist. The second is the function value has to exist there. And the third is that those two have to be equal. So this statement says this exists, and they're equal. If f of x is defined near x equals a, but is not continuous there, we say that f of x is discontinuous at x equals a. Now to illustrate this, let's look at this graph. First, let's look around x equals 1. What we can see there is as we come in from below, the limit is 2. If we come in from above, the limit is 3. Those two aren't equal, so this limit does not exist. This means this function is discontinuous here, and this is called the jump discontinuity. And the name is pretty obvious. You have to jump from here to here. Now let's look at x equals 2. Here, the limit from this side is 2. The limit from this side is also 2. So this limit is 2. The function value, however, here is 1. These two things aren't equal. This is a discontinuous function. This is called a removable discontinuity, and the reason it's called removable is if we redefine the function at one point, namely at x equals 2, slide this thing up here, we'd have a continuous function. And in fact, if you look at x equals 3, we do have a continuous function. The function value there is 1. The limit as x goes to 3 is 1. This is a continuous function. That's what a continuous function looks like. When you draw this thing, you don't pick up your pencil. It's nice and smooth. Now, if we look at x equals 4, we're going to see that when we come in from either direction, we're headed off to plus infinity. And that means that this limit does not exist. Remember that the lim x goes to 4 plus of f of x equals infinity means that the function values get arbitrarily large. So the limit does not exist. And since this limit doesn't exist, this is a discontinuous function here. This is called an infinite discontinuity. Now, let's talk about some continuity laws. If f of x and g of x are continuous at x equals a, then f of x plus g of x is also continuous there. This should remind you of a limit law of the same type, and that's exactly where this result comes from. The limit as x goes to a of f of x plus g of x we saw previously is the lim as x goes to a of f of x plus the lim as x goes to a of g of x. And because these guys are both continuous, this is f of a, that's g of a. If you read across here, it says the limit of f of x plus g of x is f of a plus g of a, which makes this a continuous function. Every one of the previous limit laws has a corresponding continuity result. The difference between continuous functions is continuous. A constant times a continuous function is continuous. The product of continuous functions is continuous. The quotient of continuous functions is continuous as long as the denominator is not 0. If n is a positive integer, a power of a continuous function is continuous. If p of x is a polynomial, p of x is continuous. And this is true no matter where we are. And finally, the nth root of a continuous function is also continuous, with the caveat that if n is even, we have to have the function value there positive because we do not want to be taking even roots of negative numbers. Let's look at some examples. Start with f of x is x squared when x is less than 0, and 2x plus 1 when x is bigger than or equal to 0. The question here is this function continuous when x equals 0? So what we do is we look at the limit as x goes to 0 plus of f of x, which as we can see here is 2x plus 1 because x is bigger than 0. This is a polynomial. You just plug in x equals 0, you get 1. When x is less than 0, we're looking at the limit as x goes to 0 minus of f of x. That's x squared. That's 0. These two limits are not equal. That means that this is discontinuous, and there's a jump discontinuity because the limit from one side is different than the limit from the other. Another example. Let's look at this function where f of x is x squared plus 1 when x is less than 1 and 3x minus 1 when x is bigger than 1. Again, we look at the limits. Lim as x goes to 1 plus of f of x is the limit as x goes to 1 plus of 3x minus 1. Polynomial, we get 2. Lim as x goes to 1 minus of f of x is the x squared plus 1. Polynomial, 2. These two limits are equal. So the two-sided limit is 2, but you'll notice that f of 1 is not defined. That means that f of x has a removable discontinuity at x equals 1, because defining f of 1 equals 2 would make this a continuous function. Now let's look at the following function. F of x is x squared plus bx when x is less than 2, and it's 5x minus b when x is greater than or equal to 2. What value of b makes f of x continuous at x equals 2? Well, the lim as x goes to 2 plus of f of x is 5x minus b. Put in x equals 2, get 10 minus b. The lim as x goes to 2 minus is the lim as x goes to 2 minus of x squared plus bx. Plug in 2, and you get 4 plus 2b. If the two-sided limit is going to exist, these two things have to be equal. We do a little algebra. 10 minus b equals 4 plus 2b. 10 minus 4 equals 2b plus b. 6 equals 3b, and b equals 2. Now that means that the limit is given by either of these things, and so that's the x goes to 2, 5x minus b. Put in a 2 for x and a 2 for b, and you get 8. But you'll notice that when you put in 2 here, you're also getting f of 2. So these two things are equal. The limit equals the function value there, and this makes f a continuous function at x equals 2. Now some terminology. If f of x is continuous at all points x equals a on an interval, we say that f is continuous on that interval. Okay, so for example, 1 over x minus 3 has a discontinuity when x is equal to 3, but is continuous otherwise as it's a rational function. So it's actually continuous on the interval minus infinity to 3 and on the interval 3 infinity. We often also say that 1 over x minus 3 is continuous for all x that are not equal to 3. Now some continuous functions. We've seen polynomials are continuous for all real x. Rational functions, which are quotients of polynomials, are continuous except where the denominator is 0. If n is a positive integer, the nth root of x is a continuous function as well, with the caveat that if n is even, we need x to be positive because we cannot be taking even roots of negative numbers. An important property that continuous functions have is that limits factor in and out. So the lim as x goes to a of f of g of x is f times the limit as x goes to a of g of x, assuming these two limits exist. If g is continuous as well, the limit as x goes to a of g of x is g of a. Okay, that's just definition of what continuous means. You combine the two, and you discover if f and g are continuous, the lim as x goes to a of f of g of x is f of g of a. And this makes f of g of x a continuous function. So the composition of continuous functions is continuous. An example, the cube root function is continuous. This is a rational function, and there's no place the denominator is 0, so this is continuous. The composition, f of g of x, the cube root of x plus 2 over x squared plus 1, is also continuous. Last, we want to talk about a really important idea about continuous functions, and it's the so-called intermediate value theorem. And what it says is, if you've got a continuous function on an interval between a and b, and you've got a value intermediate to the values at the endpoints, it's going to cross the function. So the theorem precisely says if f of x is continuous on the closed interval ab, and the value of the function is different at each endpoint, if r is any value between those endpoint values, there's a place on the interval where the function achieves that value. Now, this is an incredibly powerful little result, and we'll show you how it can be used to calculate locations of roots numerically. Our task is to show that f of x equals x cubed plus 3x minus 2 has a root on the interval 0, 1, and then to use something called the bisection method to estimate that root within 0.04. We're going to use the intermediate value theorem here, and the version of it we're going to use is we're going to assume that one of the endpoint values is negative and the other one is positive. A value that's intermediate to that is 0. So as we see in this picture here, if at one endpoint we have a negative function value and at the other endpoint we have a positive function value, there must be a root in that interval. So if we take the interval 0, 1 and calculate our function value there, at 0 we get 0 plus 0 minus 2 or minus 2, which is less than 0. At 1 we get 1 cubed plus 3 minus 2 or 2, which is bigger than 0. Intermediate value theorem says there's a root on that interval, as pictured here. The next step is to use this bisection method to estimate that root within 0.04. And we already know that the left-hand endpoint 0 on this interval is negative, the right-hand endpoint is positive. What we're going to do is look at the midpoint, which bisects the interval, and the midpoint is 0.5. And f of 0.5 we plug in and we get minus 4875, which is less than 0, and that's the only thing that's important is it's negative. F of 1 is positive, so now between 0.5 and 1 there's a root, as pictured. So we've got a new subinterval here, 0.5 to 1, and there's a root in there. Now we bisect this interval again with the midpoint, which is 0.75. We calculate f there, and it turns out it's positive. Since at 0.5 we're negative, we've now got this second subinterval between 0.5 and 7.5. Different function values at the endpoints. There's a root in there. Do it again. Midpoint is 0.625. Function value there is positive. At 0.5 we're negative. Third subinterval is 0.5 to 0.625. Left-hand endpoint negative, right-hand endpoint positive. Root in there. Midpoint is 0.5625. We calculate the function value. It's negative. And finally, since the value at 0.625 is positive, we've got our fourth and last subinterval. Negative at the left-hand endpoint, positive at the right-hand endpoint. There's a root in there. Now, we look at this fourth subinterval and we notice that the distance between the endpoints is less than 0.08, which means every point in that interval is within 0.04 of the midpoint. The root is in the interval, so the root is within 0.04 of the midpoint. And the final estimate for the root is that midpoint. So this is the thing we're estimating the root to be. And then we know this is accurate to within 0.04. Now, nobody does bisection by hand for any length of time, but you can program it. And for this particular problem, 40 iterations produced an estimate good to 10 decimal places, which is probably more than accuracy than you would ever need.